In this example, we're going to find a V0 in the network using source transformation. Source transformation telling us that we can convert part of a circuit either use a Thevenin equivalent or using Norton equivalent. The Thevenin equivalent can simplify one part of the circuit to be one power supply with a voltage source VTH with a resistor RTH in series with it. And Norton equivalent will simplify part of the circuit to be one current source IN with one resistor Rn in parallel with it. Because we can use either of these two structure to simplify part of the circuit, it also implies this one representation can be converted to the other under the requirement VTH that is equal to IN times Rn and Sm times RTH that is equal to Rn. This provided the basis of using source transformation to solve problems. By looking at the circuit, we find that the left part, this is part 1, that contains one current source with two branches of resistors in parallel. So we know that we can convert this part 1 to be one voltage source with one resistor in series. And on the right hand side, we have one voltage source with one resistor in series. We know that we can convert this part to a current source with a resistor in parallel with that. So let's call it a part 2. So step 1, we're going to simplify these two sections of the circuit first. Part 1, it will be converted to a voltage source V1 with a resistor R1 in series with that. At the same time, we know that V1 that is equal to the current 2 milliamp times the overall resistance. The resistance that is 2 plus 4 in parallel with 12. So that gives us 8 volts. And the resistor R1 that is equal to 2 plus 4 in parallel with 12, that is equal to 4 kilo ohm. For part 2, it can be simplified to a current source with one resistor in series with that. Let's call this current source have a current I2 and the resistor that is R2. And we know that I2 that is equal to the voltage divided by resistance 12 over 4, that is 3 milliamp. R2 that is equal to the resistance 4K. After we are done with these two parts, we find that part 2 that is in parallel with this 12K resistor. So we can simplify this section once more. So we simplify part 3 by using its Norton equivalent. So for part 3, so because these two branches are in parallel, the overall resistance that is equal to R2 in parallel with 12, that is 4 in parallel with 12, that is equal to 3 kilo ohm. Then we can simplify the whole thing to be the voltage source form or Thevenin equivalent. So that is V3, say R3, and V3 that is equal to the current I2 times R3, and R3 that is equal to 3 kilo ohm. The same resistance as we mentioned before. Or if you are not comfortable with using the Thevenin name, we can call this R4. So R4 will be equal to R3, that is 3 kilo ohm. And a V3 that is equal to I2, that is 3 milliamp times 3, that is 9 volts. So after the first step, in the second step, we can put all these three components back into the original circuit. To be specific, it's a part 1 and part 3, because part 2 now becomes part of circuit 3. So step 2, draw the equivalent circuit. This is V1, and this is the resistor R1. I have a 3K resistor over here, and this is what we are looking for, V0. On the right hand side, we have one resistor, which is R4, with one voltage source, V3. V0 by using Ohm's law, that is equal to the current I, that is our current I, times the resistance 3K. The current I that is equal to the overall voltage drop from this node to this node. So that is 8 volts minus 9 volts. So that is 8 minus 9 volts divided by the overall resistance, that is R1 plus 3 plus R4 times 3. So in total, that will give us a negative 0.3 volts.